Challenges in Deploying Explainable Machine Learning. It will be presented by Umang. He's a PhD student in the machine learning group at the University of Cambridge. His research interests lie in statistical machine learning, explainable AI, and human-machine collaboration. He is also a fellow at the Partnership for AI. And today, he will be presenting the research done in collaboration with Partnership on AI, specifically his work on understanding how explainability is used in the industry. Super excited about this talk.
So thank you for that warm introduction, Alyssa. As Alyssa mentioned, my name is Umang. I will be talking to you today about challenges in deploying explainable machine learning. As Alyssa said, I am a PhD student in the machine learning group at the University of Cambridge. I also split my time and spend some time at the Partnership on AI. The Partnership on AI, for those who don't know, is a nonprofit that attempts to align the AI agendas of academia, civil societies, and large tech corporations. So one of the big missions is understanding how can we build AI to benefit the people in society. Specifically at the Partnership on AI, I lead their explainability initiative, trying to understand and align the explainability research agendas of large tech corporations and academia with that of civil societies and that whole new different world of nonprofits. I also spent some time as a student fellow at the Leverum Center for the Future of Intelligence. Feel free to reach out to me if you have any questions. Twitter, email, everything will be great. And as I'm going through the talk, there'll be natural places to stop and ask, and I will answer questions then accordingly. So without further ado, let's jump into what I'm going to talk about. So in this talk, I hope to answer 3 questions. The first question is, how are existing approaches to explainability used in practice? The second, can existing explainability tools be used to ensure a model's unfairness? And 3, how can we create explainability tools that benefit external stakeholders? So each of these 3 works actually corresponds to a different paper. I'm happy, I think Alyssa will share out the links after the talk that corresponds to each of these questions. So without further ado, let's jump into the first and probably most exciting question of them all. How are existing approaches for explainable AI actually used in practice? So the primary findings that I'll report here were done with a bunch of awesome collaborators from a bunch of institutions. And this work appeared earlier this year at the ACM Conference for Fairness, Accountability, and Transparency. That work was titled Explainable Machine Learning and Deployment. So for those who are familiar with the XAI literature and the machine learning transparency literature, it's probably obvious that there's been a massive growth in the literature around XAI. In particular, there have been many algorithms that have been proposed to explain machine learning model output. So as a team, one of the things we set out to do was how can we study how organizations are actually using these algorithms? It's quite a sensible question. The earliest paper we found that was proposing approaches to XAI, where it was going back about 4 decades. So it's sensible to think that to kind of understand if organizations are actually adopting these tools. So in order to do this, the Partnership on AI, we set out to do semi-structured interviews, about 30 minutes to 2 hours, with 50 different individuals at various levels of hierarchy throughout an organization from 30 different organizations. So while we were going through this process, one of the first things we realized is that we need a shared and established language for thinking about explainable AI. So for all intents and purposes of this talk, I'm going to define transparency as providing different stakeholders with relevant information from how a model works. Now, this could be in the form of documentation on the training procedure. So you might be familiar with model cards or data sheets for data sets. This is documentation on transparency into the machine learning development pipeline. You might have transparency in the form of analysis in the training distribution. What exists in your training distribution? There's a lot of really awesome algebraic topology work that can actually be leveraged to create really awesome visualizations for end users. And another form of transparency could actually just be code releases, right? If I release all of my code to you, I'm actually being transparent about my machine learning practices. And one approach to transparency, the one I'm going to cover here, is explainability. And in particular, explainability attempts to provide insight into a model's behavior. And for all intents and purposes of this talk, we're going to define this as providing insights into model behavior for specific data points. This is actually usually called local explainability in the literature. This is not necessarily on the global meta level on like the reasoning that is learned by a model, but rather the behavior of the model at some local point. That's how we're defining as explainability. So one of the interesting things that I'll kind of add in here is when we set out to do this with a bunch of different partners across PAI, we found that a lot of civil societies actually thought of explainability as this larger framework of transparency. So there are nonprofits and civil societies that have written copious amounts of literature around explainability, but really discussing the ideas that would appear in like the model cards literature in the ML community, or would appear in the data sheets literature. So one of the things that we think is really important at PAI is actually being able to have this shared language so we can have productive conversations around algorithmic transparency around explainable AI. So once we had the shared language established with the interviewees, one of the things we asked 3 questions. The first is, what type of explanations are you actually using? Feature-based explanations, sample-based explanations, counterfactual explanations, or natural language explanations. And I'll dive into what those mean in a second. Who's the audience for this explanation? Are they going to research scientists, product managers, domain experts, or end users? And then probably the most important question is, in what context have you deployed these explanations? Is it informing some development procedure? Is there some human decision maker that is looking at this model, a recommendation and the explanation simultaneously? Or is it affecting the end user's ability to commit recourse or action, take actions in the real world based on the way the model behaves? So the types of explanations that we studied and that we found were very, very popular, the first one is feature importance. So if we take an example for a second, if I were to tell you my age, my weight, and my body temperature, and then I were to ask you if I have a fever, we'd hope that the most important feature in deciding if I have a fever is my body temperature. If it were my age or my weight, that would probably be some sort of spurious correlation. So feature importance attempts to get what we call an attribution over the inputs to basically say, here are the features that are most important. Now, by far, this is what appears in the literature as an explanation. It's probably the only form of explanation to some people and to some of the XAI community. But this is probably also the most well-studied form of explanation. The second type of explanation is sample importance. Sample importance attempts to answer the question, which of the training data points is most influential when doing prediction on a new test point? So this might be, well, your age and your weight are really similar to another individual I'd seen in the past, and so is your body temperature. Therefore, I'm pretty sure that you have a fever, right? So you're actually effectively looking at the representations that the model uses and comparing the representations of data points, training data points, to the test point. This is popularized by an approach called influence functions, which were in best paper award at ICML. Feature importance, you might have heard of certain techniques like LIME, SHAP. Those are quite popular techniques in the space, integrated gradients, smooth grad. There's tons we could list off there. And the final form of explanation, which was popularized by Sandra Wachter and co at Oxford, was counterfactual explanations, which attempt to answer the question, what do you need to change about yourself in order to change your outcome with respect to this predictor? So what do you need to change in the input? So this could be, well, I think you need to decrease your body temperature in order to not have a fever. That's a sensible sense of recourse, right? It doesn't really tell you how to do that, but it says, if your body temperature was not 100 and it was 95 degrees instead, like I probably wouldn't have said you had a fever. That exposes some portion of reasoning, but it also provides recourse to the individual in the form of what actions they can take. The interesting thing with counterfactuals is it sometimes can be quite difficult to perform the recourse suggested. So I can suggest to you, what, if you were 5 years younger, I would have said that you don't have a fever. Now that's not necessarily actionable, but it is plausible counterfactual with respect to the model and the predictor you've trained. So given these types of explanations, the next thing that we realize is who are these stakeholders that have a vested interest in machine learning explainability? So the first one is actually executives. One of the things that we found was that a lot of corporations, engineering managers and chief data scientists would tell us that their executives would ask them to start using explainable machine learning such that they can claim that their company uses explainable machine learning. There was no reason for how to operationalize on this. It was basically, please use explainable AI so I can say that we're using transparent AI at our corporation and we're responsibly deploying AI. And we found this really interesting because a lot of these senior data scientists and engineering managers actually struggled with figuring out, how do I operationalize on this? Like, what are tangible, what are concrete steps I can take to start deploying feature importance or start deploying sample importance or counterfactual explanations within my corporation's work. The second type of stakeholder was engineers. So this was by far the most popular stakeholder. So machine learning engineers, we usually use these techniques to sanity check their models, and a little bit more on that later. But by and large, it might be at a corporation you have explainable AI might not be mandated from the top. It might be a data scientist saw Scott's repo on GitHub and basically ended up forking it and started playing around with it on the machine learning models that they're training in some of their spare time. So machine learning engineers and research scientists would actually leverage these techniques to simply sanity check their model's behavior. The third type of stakeholder in this procedure was end users. So end users, if you look at any of these explainable AI papers, a lot of them claim that we want to develop explanations such that end users and decision makers trust AI systems. And after that, they'll dive into some really, really specific technique and then run an MTurk experiment on either graduate students in machine learning, or they will probably just create some ad hoc metric and then say, you know what, end users probably understand the explanations that we're deploying. And we found this to be quite surprising that almost no corporations we spoke with actually deployed explainable AI for the consumption of end users. So while it's good intuition for researchers, it's not necessarily practical in terms of deployment at the moment. The third type of stakeholder, the fourth type of stakeholder that we'll discuss is regulators. So regulators actually have a vested interest in understanding how transparent AI systems are. One of the comments that a regulator made to us is like, we could probably use these explanations to understand if a model is discriminatory or not. And this actually got us thinking a little bit, well, how can you do that? And the regulator actually was telling us that you can actually just look at the feature importance explanation to see if a discriminatory feature appears. And if it appears, then you know what, then your model is discriminatory. And effectively, if we're saying that this feature is important, we're assuming that the model has some sense of reliance on this feature. And that got us questioning, which I'll talk about a little bit later, because we ended up answering that question, and that'll be part of the second question I tackle. But regulators have a vested interest in understanding how XAI works. So you might know about GDPR, which says you have a right to an explanation. How does that kind of play out in the research community's work? So there are three major findings that we had with this work. The first is that explainability is primarily used for debugging internally. The second is the goals of explainability are not necessarily clearly defined within organizations. And the third is that there are technical limitations that make explainability very difficult to deploy in real time. So I'll jump into this first one. So explainable AI, as I mentioned earlier, is primarily used by machine learning engineers for machine learning engineers. So machine learning engineers would kind of add this on top of their existing pipelines and then basically say, you know what, like I'm just going to play around with XAI and see and sanity check my models to make sure that they're behaving correctly, right? I mean, I think most people would have intuition that for the average individual, body temperature is the most important thing when trying to determine if someone had a fever. There might be edge cases, but by and large, we can sanity check our model to make sure that that when trying to predict if you have a fever, body temperature is the important feature. Now, by and large, one thing we found is that sometimes it does move a little bit beyond the machine learning engineer. So it might go to like some internal content moderator who would be thinking about content moderation, or it might go to a QA team internally that's trying to validate the reasoning used by these machine learning systems, but it never was exposed to end users as was claimed by the XAI literature. So the primary use cases that we found in practice were mostly around content moderation, making sure that we are moderating content for the right reasons, and in finance to just make sure that you're not disparately impacting certain individuals. So the idea of explainability not being clearly defined within organizations was interesting for us because as a research community, the research agenda has it's pretty well-built trajectory, but it doesn't seem to correlate with the behavior of corporations. So one of the things we just attempt to do is, how do you actually establish these explainability goals within an organization? One thing we realize is that the first thing that most machine learning scientists actually don't start with, or most research scientists don't actually start with, or researchers, is first identifying the stakeholders. Understand who is a vested interest in consuming this explanation. Once you have that, it's really important to engage with the stakeholders to understand the purpose that this explanation is going to serve. And then once you have that, then you'll be able to devise a workflow on figuring out, well, how is this explanation going to be used in practice? So is it just going to be used to simply sanity check? Because the type of tool you develop to sanity check a machine learning system using an explanation is very different from one where you're delivering these explanations to end users alongside recommendations. And the third thing, with respect to the technical limitations around explainability, we found that there were four kind of repeated things that came up with respect to our current explainability literature. The first limitation was that there are a lot of spurious correlations that can be exposed by feature importance. So in particular, I might find that, you know what, age is the most important thing for my fever predictor. And if age is the most important feature, how are machine learning scientists supposed to fix that? So the research community hasn't actually developed a set of algorithms to actually go back and correct your model as a result. So Dan Weld and co at UW have a really fun paper that actually takes a first stab at this, but it's a long ways away from being deployed in real products at scale. I think they've deployed it in Semantic Scholar at the moment, but to get that used at scale and popularized among data scientists will take a while. The second thing is that there's no causal underpinnings to the models themselves. So the regulators and some of the executives, for some reason, really wanted to ensure that causally this feature corresponds to, like, causally affects the outcome in the real world. So in particular, we're trying to, there have been attempts to develop feature importance explanations that are causal, that are trying to explain non-causal models, if that makes sense. So there's no underlying causal model, and we're basically saying, yeah, let's just throw in a causal attribution technique on top of it. And that doesn't really make sense. And that actually is detracting, that's turning off regulators and executives from actually deploying these tools, because they know that they don't actually have any causal understanding, because the model itself doesn't have causal understanding, and we're trying to do causal attribution on top of that. But causality is important in some decision critical settings, particularly in some situations like credit lending, which had come up with some of the financial institutions we spoke with. Some of the other limitations include, like, sample importance being computationally feasible to deploy. So trying to figure out, trying to figure out which training data points are behave similarly with respect to the model is actually quite a very difficult problem. So the ICML 2017 made great progress in terms of, like, stochastic optimization of this problem, but it still requires you to calculate the Hessian, which is really expensive. Even though they use the Hessian vector product approximation, any company we spoke with that tried to deploy this struggled extensively with this. So most of them are actually unable to deploy these tools in practice. So there's a bunch of work that needs to be done in order to make sure that these tools are computationally feasible for people to deploy. And then the last limitation is there are privacy concerns that exist with model inversion. So in particular, there was work out of Moritz Hart's group at Berkeley that recently showed that if you were to expose just simple gradients of a model, you can actually invert the training data, which is actually quite scary. So that means if I gave you an infinite number of queries to just query the gradients, which is a very popular type of explanation technique of a model, I can actually just reconstruct the training data. And this actually got some of the civil societies that are focused on privacy concerned with actually providing explanations in the first place. Because if I can give you explanations, then I could just invert your model and invert your training data, which opens up a big can of worms. So by and large, the thing to realize is that there are technical limitations that make it hard to deploy. Some of these goals for explainability are not necessarily well defined within organizations, and explainability is primarily only used for debugging internally. So this actually answers our first question, which we set out to answer, which is how are existing approaches for explainability used in practice? They're only really used by developers right now, so we don't have a positive answer there, but in theory, we can actually continue to work as a community to ensure that these XAI tools make it beyond just the machine learning scientists that are using them. So I'll stop there for questions. And if there aren't any in, like, the next 30 seconds, then I can move on to the next question. Great. So I will just keep on chugging along. So the second question I said we'll try to answer is, can existing explainability tools be used to justify a model's unfairness? So this piece of work that I'll be talking about, the way I'll answer this question, we tackled this in our paper, You Shouldn't Trust Me, learning model explanations, which learning models which conceal unfairness from multiple explanation methods. This was joint work with collaborators from Cambridge, and this will appear later this year at the European Conference on AI. Awesome. I think I'm going to take that question, and then I'll jump into this. So the question is, how strongly do regulators insist on explainable models? Or are they open to non-explainable models? And what are the desiderata if so? This is a really great question. So we're kind of in luck insofar as a lot of regulators haven't developed regulation around this yet. So they haven't tried to answer this question themselves. So it's up to a machine learning community to develop explanation tools that can live on top of these non-explainable models and that can faithfully represent what's happening inside the model, such that we can tell regulators that as long as you're using certain explanation techniques or displaying explanations in certain situations, you can use a non-explainable, like very large DNN. So the desiderata are not necessarily in place, but I would highly recommend if you have time, there are some really interesting pieces of work that have come out of like the ICO in the Information Commissioner's Office in the UK that wrote a piece on, the CFPB just put that out a couple days ago as well. So they do have like very specific pieces of regulation where they're trying to go, but it doesn't necessarily say like what algorithm to use, if that makes sense. So that's technically still open to interpretation. One of the interesting things with US law that some of the regulators we spoke with is there's no precedence that has been set around this yet. So a lot of US law is case-based, and precedents might not be set for a while unless some research groups start to sue each other over models that they're building in practice to test these and like really stress test these regulations. So it's not necessarily clear how that'll play out, even though there are certain groups taking an attempt to do it. Whereas in the EU, there are a lot of organizations that are proactively thinking about this in the regulatory space as well. I highly recommend you check out this work called Accountable AI. It's by Finale, Accountable AI Under the Law, by Finale, Mason Court, and company at Harvard. It's a phenomenal piece that actually explains how our current XAI tools map onto legalese, and they make an attempt to do so, which is actually quite interesting. So highly recommend checking that out. Awesome. So with that, we'll move on to this next work on concealing unfairness from explanation methods. So the takeaway from this section will be that feature importance actually reveals nothing reliable about model unfairness. So this is kind of a Debbie Downer because this is not the answer I think most of you are hoping to hear, but we'll discuss why this is the case. So why do we even care about this problem? So let's imagine like a simple toy model that relied on 3 features. Let's say the amount of money you have, your age, and then the duration of time spent doing some downstream task. We have 2 different models and we use the same explanation technique on both of them. One of the explanation techniques tells us that the most important feature is the time spent doing the task, then the amount of money you have, and then your age. And the other model actually says, well, the only 2 important features are the amount of time spent doing the task and the amount of money you have. Age is not important, almost irrelevant to this model, locally around this point. And this is interesting because we have 2 models, let's say, that perform around the same in terms of accuracy, but their explanations are quite different for the same test point. So in theory, based on what one of the regulators told us, the model B looks like it's the fairer model, right? Because it's not using this discriminatory probably protected attribute under the Fair Housing Act of age. So we tried to study, well, can we convert model A into model B and without losing accuracy? So what really got us excited about this is that there was a lot of work that has gone into like manipulating explanations. So in particular, there's been work at AAAI, NeurIPS, and AIES around modifying explanations as a result of adversarial perturbations on the input. So you give me an input, I add some noise to it, and I can change the gradient-based explanation or any explanation that comes out the other side. There was even more recent line of work that goes into controlling explanations based on adversarial perturbations on the parameters. So I could basically take a set of parameters, add a very specific amount of noise to those parameters, and then change the explanations as a result. So what we try to do in this work is we try to downgrade explanations via adversarial perturbations on the parameters such that we can hide the unfair or discriminatory feature. So as we saw in the last scenario, what I'm basically saying is let's attack the parameters of model A such that the attribution given to model to the age feature decreases under this new model. So our setup is that we have some classifier f, which maps from x to y. We have some explanation function g, which takes in the function and some input. Let j be the feature, the discriminatory feature, the feature that you're technically not allowed to use. So this would be age, race, the sex of an individual, and so on. So our goal is to find, and let's say it's parameterized by theta, our goal is to find some delta that actually gives us the result that I was just discussing. And what are those results? We hope that this f theta of delta satisfies two properties. One is that the models are similar in output. So that means the outputs of our perturbed model are very similar to the outputs of our original model. So we enforce model similarity. And then we have low target feature attribution, which means that for some explainer G, we can actually, we want to ensure that the explanation, the attribution given to the jth feature is lower on our perturbed model than it is on our original model. So how do we actually do this? Well, we propose, So we propose a new loss function to do this, where we have this term called the explanation loss. So we take your pre-trained model, f theta, and then we basically say, well, do whatever loss you want on f theta of delta. So like, let's say do cross entropy, initialized at f theta, and then add this additional loss term, which will simply penalize the gradients of the discriminatory feature for the entire test set. And we call this the adversarial explanation attack. And notice here, we're only actually doing this for the gradients. So we're basically saying, well, you know what, just find some minima near you that is like super flat, or that doesn't actually rely on this feature. So I'll jump right into the results and get rid of and like ignore some of the machinery on how to do this. But what you're looking at here is you're looking at importance rankings. So we can take a feature attribution. Let's say you had 15 features. Here you're looking at the adult data set, which has 14 features. And we're basically saying, well, you can take those, the feature importance ranking and just rank features based on the magnitude of attribution given to them. So what we do here is we actually report the magnitudes of the important features. So in particular, what we're doing here is we're reporting the magnitude and the ranking of the discriminatory feature with respect to different explanation techniques. So you can look at like the gradients with respect to the discriminatory feature in the beginning are actually already kind of low, but with respect to SHAP and LIME, they're actually, with respect to integrated gradients and LIME, they're actually kind of high. So the discriminatory feature here being, here, I think we've done this is for age, but the discriminatory feature here actually appears higher up in the explanation. So to a regulator, this would actually be, oh, well, look, it looks like you're using age, like we ought not use this model A. And then model B, which is f theta of delta, we can, after running our attack, we actually see we can flatten out the gradients, or flatten out the explanations with respect to multiple explanation techniques. So one of the interesting things is only a few of these, so a lot of these techniques are actually variants of gradients. So we're only penalizing the gradients themselves, but in theory, you can actually penalize for any explanation technique you want. But the interesting thing we found is even when you're doing something like exact Shapley sampling, which doesn't actually rely on the gradients, you still observe this result, which is actually kind of interesting. And we don't necessarily have reasoning for that yet, but I think that's going to be really interesting direction for future work, which actually could tell us that Shapley values are, like exact Shapley values are actually just approximating the gradient, even though like techniques like SHAP would leverage the gradient, or like DASP or something, they all leverage gradients internally. But basically what this tells us is that we're able to downweight or downrank the discriminatory feature across most of our test set. So the adversarial explanation attack significantly decreases the relative importance of the discriminatory feature. This is done over the test set, so it's clearly generalized to the test set, and it actually transfers across explanation method, which is really promising, even though we just regularized for the gradients. So this is kind of scary, because this basically says that I can take a model and mask its unfairness from the explanation technique simply by downweighting its gradients. So the exact findings are in the paper, and we do exhaustive comparison against different fairness metrics, and we look at how the fairness metrics change as well, but I'll just summarize them here. The first thing is that there is little change in accuracy. Like, of course, that was one of the desiderata I set out from the get-go, but there is a detectable change in the outputs. So in particular, there might have been points that you're originally getting wrong that are now right, or points you're originally getting right that are now wrong. So that might be the saving grace for actually checking if this attack has been conducted. And again, just to reiterate, like, we achieved the low attribution we set out to with respect to multiple explanation techniques. And again, we see one of the other things that could also help us here is we still have high unfairness across multiple fairness metrics, which also could lead to interesting fairness literature, because we're now saying that there's no model reliance on this feature. However, the model is still unfair. And for those wondering, we do compare our technique to just holding the feature constant, so just setting it to 0 and seeing what happens. And if you actually look at the partial dependence plot, you'll actually see in our paper, you'll actually see that we're actually just tracking the PDP plot for holding a feature constant, except our accuracy is just going to be a little bit higher. So that's something that's a little bit interesting that we found, that like we're holding the feature constant is effectively kind of finding like some minima. We can't really say that with certainty, but in theory, we can think about it like finding some minima that is not necessarily dependent on that discriminatory feature. So our second question was, can existing explainability tools be used to ensure model unfairness? Unfortunately, at the moment, not in their current form, they can't. So we hope that there's a bunch of interesting work that goes into this direction. There was a paper at ICML last week that also continued work on this with respect to like fair washing of explanations. So I highly recommend those interested to explore a little bit deeper into our work and then the other works in this direction as well. So this is the natural place to stop for questions once again, and then I'll jump into the third section.
Hey, Umang. Just a question on standards. You know, I come from the corporate world, and we are practical people. We need to measure stuff, even if it's approximately, because, you know, we have to act in trust. And if you can't measure according to agreed methods, universally agreed methods, you basically don't have trust. And so right. My question is an agreement in the academia of how to measure explainability of a given type of model? Not everything. You know, there probably be multiple methods because there's so many very different use cases, so many different models. Mm-hmm. But for a given model, if I deploy it on Google Cloud Platform with always Google tools, and the explainability, you know, I have a result. You know, it's not fully explainable, but it's good enough. I deploy it on AWS, exactly the same model but with Amazon tools, and I get a different result. I can't deploy that. I can't use that. There's no trust in that. And so explainability, it's all about trust. Is there an agreed method to explain a given model, regardless of where it is deployed and how?
This is a really, really, really good question that unfortunately hasn't been tackled. But there is this resurgence of work in something called like predictive multiplicity, which is getting at a little bit of what you're talking about, which is that I can have one data set and I can deploy it, let's say with GCP, and then I deploy it with AWS. And let's say I use the exact same, I give each model the same amount of parameters and the same training setup on both. They might converge to different models. And unfortunately, this doesn't really help because this basically means I have two candidate models that look equally good, but their outputs differ. So in deciding to use one of them, I'm actually going to disparately impact some individuals. And if I decide to use another model, I'm going to affect some individuals that, let's say I would have granted the loan, I'm not going to grant it anymore, right? So we're actively working in this exact direction, and we basically there are techniques that academia is still trying to figure out how to make it work, where I can guarantee the optimality of the model that you've deployed, right? I can basically tell you that this model is the best you could possibly do. When you have really large over-parameterized deep learning models, so if you're using really, really big networks, like you're going to suffer from this problem where you'll have like, where multiplicity will exist. So the example I like to give when talking about predictive multiplicity is like, if you gave me 10 training data points, and then you gave me an infinite number of parameters to fit to those 10 data points, I can get you 90% accuracy 10 different ways, if not more.
Yeah. I fully understand what you're saying.
And the question is like, how do you pick which one? And I agree that there isn't necessarily a way to do that, but just backtracking into like the first part of your question, I think hopefully that answers the second part of what you were talking about. The first part of your question around metrics. So what you could do is actually just plug an explanation technique on top of the model you've trained and look at the explanations and then deploy accordingly. So it actually gives you a sense of, well, let's just look at the explanations and deploy the model based on the explanations we like the most. So in order to do this, you need to have evaluation criteria for your explanations, which aren't very much agreed upon in the literature. However, there is some work in this direction. I'll have Alyssa send out another work that we have appearing at IJCAI this year, which just answers this question for feature importance explanations, which I said were the very popular type of explanations. We just collect and aggregate a large list of those and then study the behavior of each of those, each of that work. So it's interesting. So I'll have, Alyssa we'll find that paper and send it your way. So there is work on evaluating explanation techniques that sit on top of models.
Thank you.
Cool. I see Bernice has a question. Is really interesting your gradient approach. We see fooled explanations with Paul perturbations in this. Yeah. So Hima's work was like we're concurrently working on this at the same time. I think they built like a scaffolded classifier that sits on top of it, on top of like an existing classifier. What we're basically doing is we're just perturbing the original model. I guess there are different ways of going about the same thing. And there's another work at ICML that wasn't hers this year called, it's like fair washing something from Klaus Robert Mueller's group in Berlin. And they basically studied literally the exact same problem that Hima's group and our group are studying. But effectively, I think our results are effectively the same, that we either need to build tools that are like robust to these kinds of attacks, or just basically flat right, like get a megaphone and tell everybody to stop using explanation techniques to justify a model's fairness or unfairness.
Yeah, awesome, cool. I might want to talk to you offline about that at some point.
Yes, definitely. Please do shoot me a message and we can talk about it. Thank you, Jiaho. Oh, really nice to see you. Yes, this is the one, fair washing explanations with off manifold detergent. It's a really, really strong paper as well. I'm not sure if I missed another question that might have been there in the chat. Alyssa, was there one I missed?
I don't think so.
Great. Any other questions?
I had a question. So I think, so I used to work in the self-driving car space.
Awesome.
And like, it's kind of a very hard space when you combine explanation, policy.
Of course,
but at the end of the day, it's like you need, like a lot of companies are tackling them in different ways. Like some of them are saying like, are we just better than a human driver?
Yeah.
But then like, you don't have enough data set to know what a good human driver even is, right? Like, it's like that variance is very wide to, like, but you could be better than a human driver, like a certain class of human driver. So I think, so how do you all like think about this sort of, it's kind of an end-to-end problem for like explainability in that sense, because if something happens, like liability, insurance, like it just ties into so many different like aspects of society as a whole, like economics, policy, like machine learning, AI, like safety standards in like automotive. So I just wanted to hear your thoughts on like, how does all of this tie into like a more practical application of like so many things intersecting? And because they claim that they are launching self-driving cars like next year, and that next year never comes up. But I think that kind of, I wanted to understand like where on that spectrum do you think an application like self-driving cars can actually think its way through this like kind of chicken and egg problem, because it's sort of they're stuck because they're not launching because of all these like safety, like regulatory concerns, and it just seems like it's a research project, very well funded research project, instead of something coming on the street, right? I think that's kind of where like I'm feeling that vibe in some ways, but I just want to hear your thoughts on.
Yeah. I just a random plug. I think one of the as much as it is a small research project, I still like distinctly recall during my time in Pittsburgh, when I was doing my undergrad there, we would call an Uber at night and we'd get a self-driving car sometimes. So it is in practice in some places. I agree that it's not necessarily at the scale that we would desire. I imagine there might be other people on this call that have like had similar experiences, but how do we get to scale? I think that's a really, really interesting question. This actually kind of ties into the next question, which I think is like, we've kind of pigeonholed ourselves into this definition of explainability, which doesn't actually answer anything or isn't helpful for an end-to-end pipeline, or isn't actually helpful into for anything practical. So one of the things is, how do we develop, first of all, how do we understand what needs to be explained, or what's like the minimal amount of explanation needed for us to be able to deploy the system? So there is like a lot of really awesome work on the software engineering side and like root cause analysis. So what is going to be a root cause analysis analogous for ML pipelines, right? When I have these models that are just chained together, right? Like you have like hundreds of models that are running in a Tesla autopilot, hundreds of models that are running in any self-driving car. How do you actually do root cause analysis? Simply to either identify the model that is erred, or to really get the sense of like where in that model that error lies, right? Which is kind of the question we're stuck on. It's like, I have a model, the model is living in some utopian silo, and I will just basically say, here's why you're wrong, or here's what's going on under the hood, right? But I think your question is an extremely sensible one that our community needs to like zoom out and think about at scale when models are interacting with each other. What types of explanations are simply needed to make sure that the ML models we're training are getting out into production? And Alyssa is answering interesting questions like this as well, right? Right, on making sure that we understand and monitor these models in production. So unfortunately, I don't have a good answer to your question. I think what Javi's talk, when he goes second, he'll touch on some work that we have in this direction. There's work that like Yaron Gal has in this direction as well, basically on like identifying like where, like it might just be enough to tell you what I don't know as a model. And that might suffice as a form of explanation. So you might just need to pass some regulatory like benchmark for saying like, oh, as long as you know XYZ, I don't care if you don't know ABC, right? And then we'll let you deploy that system. So we're very far from that, but that might be a different approach than the one we've currently been taking.
Yep, thanks for that perspective.
Awesome. So with that, I'll jump into this last portion of the talk, which is how do we actually, again, I think going right off that last question is how do we actually create explainability tools that can be used by external stakeholders and move beyond developers? So this work is called Machine Learning Explainability for External Stakeholders. It was based on a closed door convening that was hosted by the Leveroom Center for the Future of Intelligence, the Partnership on AI, and IBM. And this work appeared at a workshop at ICML earlier this year, and it's available for everybody to read online. So the overview of what that workshop was is we basically had 33 participants from 5 countries convened in New York in early February. 15 were machine learning experts, 3 designers, 6 legal experts and lawyers, and 9 policymakers and regulators. Their domain expertise varied from finance, healthcare, media, and social sciences. And the goal was, can we facilitate some sort of inter-stakeholder conversation around explainable machine learning, right? So this is kind of going in the direction of that last question. Is like, look, we can't do this alone as just the ML community. We can't do this alone just as the computer science community or just the computer science community talking with the regulators. It's really an interdisciplinary end-to-end project. So the 2 major takeaways I have from this section, which I'll just summarize, is one is that there's a need for community engagement in the development of XAI. And the other one is that there's some nuances in deployment of explainability. Probably both are obvious in the tone and the words I've been using before, but I think what I'll do is I'll talk about these takeaways as questions for a community to answer. And hopefully some people on this call and beyond can help kind of tackle these really pressing questions for us. So with respect to community engagement, there are 4 things that we'll discuss here. The first is it's really important to know in which context the explanation is going to be used. And does the context change the properties of the explanation we expose, right? do someone really care what feature is being used, or they simply need to know that their model is reliable, right? Maybe the regulators simply just need to know that this model works 99% of the time on when it's generalizing on the test set. Like we can, and assuming you've put together a good enough test set, let's just let this model run free. That might suffice based on the context. So in some of the, thinking about some of the fairness implications of this work, like if we lived in this world where we only had squares and we built a square circle classifier, and we had 99% of our training data set was squares and 10% was, and 1% was circles. And then if we had a guarantee, now this is really hard to say, but if we had a guarantee that at test time and when deployed in the wild, we're only going to see that same distribution, there's no harm in deploying that model, right? But if we live in a world of equality, then we need to make sure that we don't deploy this model because it hasn't actually seen like 50% squares and 50% circles as it might appear as it might get at test time. So simply understanding and taking time to understand the context in which the model and the explanation that are going to be used, like that is actually really helpful for understanding what type of explanation, if at all, you need to expose. The second question, which goes off to previous questions, how do you actually evaluate these, both quantitative and qualitatively? We've taken a stab at this in establishing quantitative criteria for this, but also qualitatively, like what are these, do these explanations suffice for displaying a model's trustworthiness? And it's not necessarily clear that we have that we have consensus around this. There have been approaches that discuss this. So Jen and Hannah at Microsoft Research have done some really interesting work around qualitative evaluation of explanations, as have the folks at Google and Harvard. I will try to send those links out to Alyssa so she can find those papers and send them to you, to everyone here. But that's on qualitative evaluation, and then quantitative evaluation criteria. We really need consensus around that. So that was hopefully that was one of the goals with the paper that we worked on for IJCAI. Because if you look at any of the explainable machine learning papers, you'll find that they all define their own metric, and then they show that their technique does best on the metric that they've defined with respect to all the other criteria. That's not necessarily productive. So agreeing upon a set of metrics and then evaluating our explanations in some way, and basically using community engagement and qualitative techniques to ensure that doing qualitative studies to ensure that the explanations are evaluated in the way humans want them to be, is going to be really important. The second is, can we actually prevent data misuse and like preferential treatment that might occur to some affected groups? So one of the things that we found is that a lot of these machine learning models and even explainability is built without the affected groups involved. So I really love the Diverse Voices project that UW Tech Policy Lab runs, because they're trying to reverse that narrative. But a lot of that, there's a lot of room for data misuse and preferential treatment if we were to just deploy explanations as is. So some folks were thinking about this in the if you're applying to get an apartment and submitting a rental application, if you're working with an agent and not just applying on your own, like there might be preferential treatment because the agent might get an explanation from the model that denied you the rental, and they might be able to convey that back to you so you can change and commit some recourse to ensure that you're approved for that apartment next time. So it's not necessarily clear that there'll be some notion of like equal access to explanations once we deploy them. And the other, which I'm very, very keen on, and that's one of the reasons why I was really happy when Alyssa reached out, is like, can we actually educate external stakeholders and data scientists about the functionalities and limitations of explainable machine learning? So for external stakeholders, it's first realizing that you even have an explanation at your disposal. So there's been a lot of work in the consent space around like making sure you have some sort of, you convey to end users that they're interacting with AI systems. But you can even go further and say like, look, you have the right in some sense to get some sort of justification or explanation from this model. You should be able to you can ask the organization that's deploying this AI system to say, give me an explanation for why you're treating me the way that you're treating me, right? And there are some companies that have done this. I mean, if you look at what Facebook has done with Why Am I Seeing This? That feature, we had a collaborator group at the Max Planck Institute in Germany actually go and buy advertisements for very, very specific groups of people on Facebook ads. And they'd be like, I want to target 55-year-old males who visited this ice cream parlor and live in this county in the United States of America. And then they'd go create profiles for those individuals and look at the advertisements they got, look at the explanation that say, why am I seeing this advertisement in my newsfeed? And you'll see it says, because you're within 18 and 60 years old and you live in the United States of America. So educating people that you even have access to it, and then saying that there are limitations with getting access to it is really important, right? So it might not actually be faithful to the model. So that's why evaluation criteria and the regulation around this and being able to share this information with regulators is really important, which makes this a really necessary interstakeholder project. And then also being able to convey these limitations to data scientists. So the thing I was just talking about with algorithmic fairness, like we were able to share that with regulators. We were able to share that with data scientists, such that when if someone at your organization comes and asks you, can you use this to justify unfairness, you can basically say like, we ought not do that because of XYZ reasons, and it's like been shown in the literature that this can be gamed. We don't want to be pinned for that. So community engagement is really important when developing explainable ML tools. And then when deploying XAI, it's really important that we move beyond the current definitions of explainability. So the first thing that there's a really interesting open question, which will be the topic of what Javier talks about right after me, is how does uncertainty in the model, and perhaps even the uncertainty introduced by some approximate explanation technique, result in different explanations, right? So the model itself is uncertain in most cases because you're using some sort of probabilistic model, and like I'm not necessarily sure that all data points are treated equally in this model. So how do you expose that uncertainty as an explanation to other people? And then more importantly, if you're using an approximate explanation technique, how does that affect the explanations at the end? So if you look at the SHAP repo and like the work that SHAP or Lime does, those are both quite approximate. They're very, very, you can make some changes in the input, you can make some changes in the parameters and change your Shapley values a lot. So they come with nice axiomatic guarantees, and for some reason the machine learning community has fallen in love with that. But as soon as you start doing approximations, like all of those axiomatic guarantees fall apart. So like, why is this important even in the first place? So the uncertainty introduced by the model and by the explanation technique are important to keep in mind when deploying. The second is how do you stakeholders interact with the resulting explanations? And then can we actually treat explanations as a way of interacting with your model? So can you improve your model if you know that your model is focusing on the wrong pieces of information? So there's a handful of works that are trying to go in this direction, but there is a dire need for people to start working on this problem, because this is what is currently keeping explanations from being deployed in practice. Because if I know an explanation is wrong, I can't really make any changes as a data scientist, let alone as an end user who wants to contest a prediction. And then how, if at all, will stakeholder behavior change as a result of the explanation? So this is something that we hadn't really thought much about. But if I'm giving you a counterfactual explanation and I tell you that you need to go earn $100,000 more, and then maybe I'll give you this loan, what will happen to human stakeholder behavior in the real world? Like, we're suggesting some sort of intervention, which may or may not cause some sort of drift in our training distribution, because we're not going to see, if we're suggesting everybody make $100,000 more, and then how does that change the people we see at test time? And it's not necessarily clear the connection between that distribution shift and the explanations that are shown. Hima, I think Bernice was mentioning this paper, there's a more recent work that she had at Hima Lakaraju, she had more recent work at ICML, which started studying this problem of distribution shift of explanation. But again, it's so preliminary that there isn't something that we can say, here's what the data scientist community can do as a result of, to preempt behavior change as a result of explanations. And the last is, over time, if an explanation technique is deployed and stakeholder behavior changes, do we really need to go back and update either our explanation technique or even update our model, right? Because again, if stakeholder behavior has changed, then we need to be aware that stakeholder behavior is changing and then maybe make updates accordingly. And all of these things are extremely context dependent, which is why it's really important to have that, to when you're developing the model, to have community engagement. And then from there, when you're deploying explainability, you can kind of create this iterative cycle of making sure the community is engaged in the explainability work that you're doing. So all in all, there are two takeaways from this. One is that you need community engagement, and the second is that there are nuances to deploying explainable machine learning, and future directions are, there are a lot of ripe future directions for work in the space. So how can we create explainability tools for external stakeholders? One of the things is I think this is the big positive. Community engagement and thoughtful deployment are like the #1 ways we can make sure that explainability tools are actually consumed by external stakeholders. So in all, I answered 3 questions. Explainability tools are mostly used by developers. They can't be used to justify model and fairness in their current form, and community engagement and thoughtful deployment of XAI are really important. So in all, this talk was titled Challenges in Deploying Explainable Machine Learning. Thank you so much for listening. Feel free to shoot me an email, reach out to me on Twitter. I'm more than happy to take any questions. So that'll be all.
Thank you, Umang. This was fantastic. Let's do a few questions really quickly and then make sure that we switch to the next talk before Javier falls asleep. So anybody wants to jump in really quickly with questions?
I had a very basic question. I just want to understand for like the different stakeholders that you have encountered, what are the incentives, like overall incentives for explainable AI? Because I think for a corporation, it's different. For an engineer working on it is different, but for a policymaker, it's completely different, right? So what are the, like, is there something that you could like weave out of all of them as this is a shared incentive versus like, are we trying to overly generalize the problem, or just we can start tackling each branch of the problem specific to the stakeholders?
So unfortunately, I don't have an answer to that question, but we're answering that exact question at the Partnership on AI right now. So if you're interested in that, we're literally studying this to create this mapping for the community, because this is of utmost importance. And I can even prelude that by saying that it's going to even be domain and even model specific, right? So like if you take an end-to-end model, like driverless cars is a lot for a second, but like, let's say you took driverless cars and like for driverless cars, what are the individual XAI incentives for each of those groups? And it might even be for something really specific. So within finance, you might have to just deal with credit risk models, or you might have to just deal with, in healthcare, like a diagnostic system that's only predicting one particular disease, right? Like it is really context and model specific. So unfortunately, I don't have an answer to that question, but if you're interested, do reach out. Like we're literally answering this. We're trying to develop an answer to the question right now.
Awesome. Thank you.
Yeah, I see there's a question from Abhishek, if you want to tackle that, and then we'll move to Javier.
In critical cases like finance, healthcare, do you have a sense of what decision aid models are passed on to users, an outline of how they should be used? Okay, so I'll take the first question first. So there is an awesome amount of work that I think is really underappreciated in like the like human AI complementarity work, which really tackles this exact question, right? Which is how do you take a decision support system and deploy it, and like what are the requisite things I need to tell you about that model such that it can be deployed. More interesting work coming out of Dan's group at UW is basically on studying how what happens if I were to show you an explanation, show you the model confidence, or show you some variant of an explanation, and then asked you to do some downstream task alongside the AI system. Because in actuality, there are 2 types of models. I guess you can think about models as making decisions by themselves autonomously, which rarely is deployed, and then models that are assisting humans as they're making decisions in the real world. And these are, I'm purely talking about supervised learning here, but in those situations, the decision support systems that we're using, there is a great body of work that is out of scope of what I was talking about that tries to answer those questions. And how populated or strong guiding are these recommendations? Unfortunately, not strong enough. So we have consensus perhaps in some of these communities on how we should treat models, but there isn't necessarily regulation or even laws around how this should happen in practice. So we're a long ways away from that, but it's important that we do like take an interdisciplinary approach to this, so we can say, well, we really want to deploy XAI in this context end to end. So make sure policymakers are on board, make sure developers are on board, executives and corporations, regulators, everyone's in place such that we're all in alignment, or we basically work towards alignment, such that we can actually deploy this for the first time, these decision-aided tools at scale, instead of just having like one-off experiments or one-off projects. So I'll be here around to take more questions at the end, but thank you all for listening. I appreciate it.